So course outline. Actually, in this course, we will learn how to analyze the power flow, and then how to calculate the current flow in the lines based on the specific load. So we will focus on the power flow. Some books use power flow, some books use the load flow analysis. Actually, all about the calculation of current voltages at all buses. Okay, on the power system network. Last time we learned how to calculate current voltages at the specific bus bar, but this time we will focus on more complicated network. Okay, so we will study power flow and then calculate the fault analysis. We will review our previous study with the balanced faults, and then we will study how to calculate the unbalanced faults analysis. Okay, so this is the course outline. This is a single line diagram. We can use many power system software to analyze or to do the power flow analysis, okay, load flow analysis. So this is a ETAP software. We can draw the incoming bus bar or feeder network. This is bus bar, and this is a single line diagram. We can do the power flow analysis by using the software. But for the beginning, we will study how to manually calculate the power flow based on the specific loads, load at the load bus bar. Okay, load bus. So this is course content. Actually, the first chapter will be cover the introduction of the power system. When I look at the slide, actually most of the materials has been covered in the previous electrical power system subject. For example, from the generations, how power is being generated using the hydro, steam turbine, solar, and so on. And then how power is being transmitted. We use high voltage transmission. Why we use high voltage transmission? Because to reduce power loss, reduce voltage drop, and so on. All that topic has been covered in the electrical power system subject. So I will not go in details for the chapter 1. You may refer to the slide okay, that has been uploaded in the column. Okay, and then for the chapter 2, this is the main topic, power flow. So power flow. Before we can analyze or do the load flow analysis, we have to construct the bus admittance matrix. Admittance is actually the inverse of the impedance matrix. So we have to find impedance. Impedance is Z let's say this one. Okay, we have Z impedance from bus bar 1 to bus bar 2. So we can find Z or Y, or how we can say admittance. This is admittance. Admittance is inverse of the impedance. This is impedance. Let's say we have two bus bar. This is generator. We have bus bar 1. We have another bus bar 2. Bus bar 1, bus bar 2. This is our Z impedance. Z from bus bar 1 to bus bar 2. Okay, so first step to do the power flow analysis is we have to construct the admittance matrix. Okay, to construct this one by using the impedance value. So we take this impedance value, we inverse this impedance value to get the admittance value. Y12 is equal to 1 over Z12. And this is the beginning of our analysis for the load flow analysis. Okay, so first we will see how to develop the bus admittance matrix, and then we will learn how to solve the power flow solution by using the equation. So we have 3 methods to solve the power flow analysis: Gauss-Seidel methods, Newton-Raphson methods, and fast decoupled methods. This is 3 methods can be used to solve the power flow. Okay, we will see later lah. Okay, this is for chapter 2. Chapter 2. So for chapter 3, we will learn how to calculate balance fault. So in the previous in the previous subject, EPS, electrical power system, EPS, we have learned how to calculate the balance force. Okay, balance force. So balance force is a force occurs on the three-phase line. This is balance, or three-phase to ground. This is a balance force. Okay, we have two type of force: balance and unbalanced force. Okay, for balance force, usually balance force is three phases or three-phase to ground. This is balance. For unbalanced force, other than this lah. So let's say we have one line to ground, one line to ground, or line to line force, or line to ground. This is unbalanced force. Okay. In the previous subtopic and in the previous subject EPS, we learn how to solve balance force. But in this chapter 3, we also we will learn how to calculate balance force, but by using the bus admittance matrix. Okay, this bus impedance matrix. Sorry, bus impedance matrix. Last time we just calculate by using I force equal to V force over Z force. Okay, but now we will use bus impedance matrix to calculate all force current on the specific bus bar. Okay, this is chapter 3. For chapter 4, this is chapter 3, chapter 2, this is chapter 4. In chapter 4, we will study how to calculate unbalanced force. As I mentioned earlier, we have three types of unbalanced force. We can divide unbalanced force into three categories, which is single line, line to ground, line to line, or line to ground. These three types of unbalanced force. Okay, in chapter 4. To solve this unbalanced force, we have to know the sequence impedance, and then this is the compulsory that we have to know what is the sequence impedance. So we will study later what is sequence impedance. Actually, we have three types of impedance: zero sequence impedance, positive sequence impedance, and negative sequence impedance. These three type of impedance that will be used to model our network when this type of faults occurs. Okay, so this is the main topic in this subject. Okay. This is the outcomes of this subject. We have 4 course outcome. So the first course outcome is at the end of this course, students should be able to apply knowledge of electrical power system fundamental to the solution of complex electrical power system network. Okay, this CO1. CO2 is students can develop power flow solutions. Okay, power flow solutions considering faults. Okay, if any, in power system network. This CO2, CO3. Okay, this CO1 and CO2 usually will be covered in test and final exam. Okay, so this one is theoretical. For CO2, students should be able to develop power system study under steady state condition using power system software. Okay, this is usually covered by assignment and project. Okay, so usually this for project or assignment 30%. Okay, this one 30%. Okay. So CO4 is relate the works of engineer with the ethics and professional. Okay. And this is for CO that will be covered in this course. If we look at the assessment, okay, we have 4 assessments. 10% come from the quizzes. Okay, maybe we will do for quizzes through Kalam. Okay. So student can answer the quiz in Kalam. And then we have one test, only one test. Okay, one test that will be covered chapter 2, power flow analysis. So actually chapter 2, they have 3 techniques to solve power flow: Gauss-Seidel, Newton-Raphson, and fast decouple. These 3 methods can be used to solve power flow. So students should understand these 3 methods to score this test. Okay, because we only have 1 test. For the test, only 20%. Okay. Next, we have project or assignment. This project or assignment will be cover 30% of your carry mark. Okay, so 30%. This usually for the assignment or project, you will use one of the power system software. Usually we use ETAP. Okay, so this ETAP software. For me, I usually familiar with the PSCAD software, but for ETAP also we can study together. Okay, ETAP for power flow, because they have many other software can be used to model our power system network. Okay, so and finally we have final exam. Final exam 40% will be cover chapter 2, 3, and 4 power flow and for analysis. Okay, this is our assessment. So if we look at the percentage, so CO1 cover 20%, CO2 50%, CO3 10%, and CO4 20%. Okay, and this is a software that can be used in our analysis or our modeling for the power system network. Okay, we have ETAP, power analytics, SKMM. Last time when I study my master, my friend said this SKMM is being used by the TMB at that time, but now I don't know what software is being used by TMB. TMB use this one to model a system and study the power flow. Okay, then we have this one, PSSE, power system simulator, ETAPS, and many more. We have big silence. MATLAB also can be used to study power flow and so on. Okay, we have PSCAD, EMTDC, and so on. This some of the software that can be used, okay, in our modeling and analysis. So maybe you can start to explore this software, which one can be used for the power flow studies. Okay, so this is the example. We have the power system distribution network. We can model all this network in any software usually. So in this case, I don't know which software. Maybe they use ETAP, okay, to model the power system network like this for incoming bus bar and then this circuit breaker, transformer, and so on. So actually, why the power flow study is very important? Actually, before we do the expansions or we connect other loads to the system. Let's say this is the power system network in the distribution system, one of the distribution system in Malaysia. Let's say suddenly there is one new university will be developed, let's say nearby to this distribution system. This university need to get power supply. So let's say this university need to get power supply from this bus bar. So we have to analyze the system, this network. Either this bus bar or this transmission line can be used to supply this new load. Let's say this UITM, new UITM want to open new branches near to the UMP, let's say. So this UMP is taken from one substation, take the incoming power from one substation. If this unit UITM want to take power supply from the same substation, we have to study either this substation can supply this much of power to the UITM. That's why we have to do the power flow analysis. We have to know what is the maximum current will be flow in this line. Either the transformer over here can withstand the maximum power to this load, to this new load. If cannot withstand, what size of transformer is suitable need to be used to supply to the new load. That's why transformer we have MVA, right? So this MVA actually the capacity of the transformer. Transmission line also they have the capacity of the current flow. What is the current flow in this line? Either this cable can withstand the maximum current flow when the new load is connected to this line. So that's why we have to do the power flow. And then we have to calculate current, voltage, current, power, and so on. So that's all the equipment are well selected and are capable to supply the power to the new loads. Okay, that's all power flow analysis all about. Okay, that's why power flow analysis is the backbone of the power system studies. Before we do the fault analysis, we have to do the power flow first. Okay, either we want to study power system protections, how to select the circuit breakers, how to select the cable, transformer size, and all others power system equipment. We have to do the power system analysis first. Okay, that's why this is very basic analysis and very important. Okay, to the power system engineer. This is some of the engineering standards. Okay, that can be refer when we want to do the analysis, especially for the power flow analysis and so on. Let's say this is a standards from IEEE, recommended practice for power system analysis. This is for circuit breaker, short circuit current, and so on. They have many other standards from IEEE, and then also from the ANSI, American National Standard Institute. And then we have some from the NFPA, Protection Association. These are all the standards. Usually we have to refer when we want to do the studies. Okay. Okay. So this is our references book. Okay. So reference. Usually the main reference is I use this one, Hadis Adat, Power System Analysis, because during my study last time in UTM, my lecturer used this book. Actually, until now I use this book for power flow, electrical power system stability, and so on. I use this book, Power System Analysis by Hadis Adat. Okay, but you can use other references. This one also can be used. Modern Power System Analysis by this author, and so on. Okay, but sometimes the terms used by different books are quite different. Maybe in this book they use power flow analysis, some book use load flow analysis. Yeah, only that's the difference. The rest is the same. All need to solve the power flow analysis, power flow analysis, PFA, or load flow analysis. Some will use load flow analysis. Okay, all these analysis actually to calculate power, current, voltage, and so on at every bus bar of the network. Okay, this is what is this? This is the previous result. Okay, because this one has been shared by the previous lecturer, so I just show to you now. This is a result from the semester 2 session 2016 2017. Okay, this is the result. Okay, for the power flow power system analysis subject. 3 students fail, 2 students score, and then this session 2017 and 2018 So still have some student fail. It's not many lah, only 1 or 2 students. 1 F for E. Some of students fail and some students are excel in this subject. Okay. So by looking at this graph, we can say that this subject is can be scored depending on the student's effort. If you are usually I will draw like this. This is our generation. We have generator, we have transmission line, and this is the transformer, transmission line. We have this bus bar, this load. Okay, this the generation station, generator. This one transmission. This one distribution okay, and this one load. And this is a basic power system network. Usually we will have the generations. We will generate power using quite high voltage sorry, it's not zero, up to this voltage up to 20 kV okay, and then we will step up this voltage, let's say this 20 kV up to, maybe in Malaysia we have maximum transmission line is 500 kV, and then we will step down this 500 kV towards maybe around 33 kV before we step down further 33 kV to the 11 kV at the distribution center. Okay, so if you look at this network, we have generator 20 kV, then we step up the voltage using high voltage transmission, and then after that we have to step it down by several transformers. Actually we don't have one transformer, we have several stages, 500 kV, 30 kV, 33 kV to 11 kV and so on. But in this case, to simplify the network, we just use generation, transmission, and distribution. So if you look at this, I just want to review the previous electrical power system subject. I always say that why we have to use high voltage. I always say that the importance of high voltage is to reduce power loss, reduce voltage drop, reduce cable size, and reduce cost. This is 4 points that you have to remember all the time, because this is the basic question that will be asked when you try to apply for the engineer, especially in the TMB. They will ask you, why we use high voltage, why not use low voltage, why we have to spend money to buy this transformer. We don't need this transformer actually. If we can have the efficient transmission system without losses, we don't have to use this transformer. But now the transmission line losses is the highest losses in the power system network because transmission line is very long. Losses on the transmission line also is very high, especially when we use low voltage transmission. That's why we have to step up the voltage. When we step up the voltage, when the voltage is high, we can reduce the current. This current will be low. So power loss, P loss is equal to I square R. When current is low, we can reduce the power loss that's occur on this transmission line. Okay. This is the previous topic and then in EPS. And then we have Then we have per unit system. And this is the important topics that you have to revise. You have to refer back to the electrical power system subject. So the per unit system, let's say Z per unit. Usually, when we look at the power system network, something like this. Okay. All the data is given in percentage. Let's say X is 0.1%. Sometimes they use percent. Sometimes they use 0.01 per unit. This is all actually refer to the per unit value, refer to the its own per unit value lah. That's why we have to know what is the per unit value. Per unit value is actual value over Z actual Z base. And this is basic. This is basic per unit value. Refer to its own rating. So that means if this SG for the generator 0.15%, actually this is S per unit for the generator, refer to its rating. Let's say this rating is 100 MVA. Okay, wait 4 minutes because my kids are making some noise. Wait. Okay, so we continue. So Z per unit, actual over base. Usually you have to remember and you have to know this is actually S per unit refer to its own rating. Its own rating, that means this, if this generator rating is 100 MVA, 11 kV, this rating refer to this value and this value. This per unit rating is refer to the transformer value. So usually we have to convert this rating into the new per unit system. New per unit value. Okay. That's why we have to convert to the new per unit value. But usually in this subject, to simplify the calculation, we will give the network with the per unit or new per unit value. Okay. Just to simplify. So we don't want to test you on how to calculate the new per unit value, but we want to test you on how to calculate power flow. Okay, that's why we give you all new per unit value. This one new per unit, referring to, let's say, 100 MVA. And maybe 11 kV on the generator sides or so on. Okay. Usually we will give you this value referring to the new base to simplify the calculation. But in the real life, usually you have to calculate the new per unit value for all the power system equipment. Okay, generator, transformer, transmission line, loads, motor, and so on. Okay, so please spend time to look back at your previous notes, electrical power system notes. Okay. Okay, so that's all. Okay, so that's all for the introduction. Okay. So okay, introduction. So any question? Maybe we can see the chapter 2, bus admittance matrix, maybe. Power flow analysis. So first subtopic is bus admittance matrix. As I mentioned earlier, before we can do the power flow analysis, we have to develop the bus admittance matrix. Admittance means Y. Okay, this Y is come from impedance Z. Y is actually the inverse of Z, 1 over Z. Let's say we want to find Y admittance from bus 1 to bus 2. Actually, we can find 1 over Z from bus 1 to bus 2. That's how we find the value of Z Y12. Okay. So outline for this chapter: bus admittance matrix, power flow, solution and equations, Gauss-Seidel, line flow, losses, Newton-Raphson. This is method lah. Gauss-Seidel, Newton-Raphson, and fast decoupled power flow solution lah. These 3 methods to solve the power flow or load flow analysis. Okay. First step is developing the bus admittance matrix. So this introduction lah. Power flow study can be referred as the load flow. Some book use load flow, some book use power flow. This is the backbone of power system analysis and design. Why? Because we have to know our system is stable lah. Okay, we do the power flow analysis to look to see either our system is stable or not lah. Okay, check all the equipments in the range of the capacity lah. Let's say for the transformer we have TX this TX 100 MVA. So power flow through this transformer must within the limits, must below the transformer capacity lah. That's why we have to run the power flow to see this transformer is overload or not. Transmission line, and this one we have circuit breaker. We have to select the right size of circuit breakers, right size of transformer, right size of cable, and so on. Okay, that's why we have to run the load flow. Okay, that's why usually we say the load flow is the backbone of the power system analysis. Okay, analysis of power. So analysis of power system is in a steady state operation. Why steady state? Because we only take one value of the load lah. This is load. Let's say this load lah. Load is always changing. Okay, load is not static load, depending on the users or the consumers. Sometimes load is increasing, sometimes load is dropping. Usually load is increasing during the working hours, and then load will decreasing towards the night, early morning lah. Okay, that's why we have studied steady state. That means we take one value of loads at the specific load, and then we study the power flow at that specific load size. Okay, we study on the steady state. So what we have to find when we solving the power flow, actually we want to find this parameter: voltages at each bus bar, current flowing in each line, real power flow, and reactive power flow in this. Let's say we have 3 bus like this. We have generator, we have bus bar. Bus bar is this load, this is generator, this is another transmission line, this transformer, and then transformer lah. Okay, so if we have this network, 3 bus system like this is one bus bar 1, bus bar 2, bus bar 3, 1, 2, 3. This load size, let's say 100 MVA. This load. Based on this loads, how much power this G1 must be produced and G2 must be supplied, okay, to supply this size of load. Maybe this one half from generator 1, half from generator 2 lah. So based on this situation, we have to calculate voltages at this bus bar 1, bus bar 2, bus bar 3 lah, and then we have to calculate current flow in this line, in this branch, 1 to 2, 2 to 3, and 1 to 3. Okay. Current, and then also power flow. In EPS, we didn't calculate power flow. EPS, we just calculate I and V. But in the subject, we will calculate what is the value of the real P and reactive power Q flowing in this line. Let's say for P from bus bar 1 to bus bar 2. Q from bus bar 1 to bus bar. So we have to calculate all these values. Okay. And then so on bus bar 2 to 3 and 1 to 3. We have to calculate the power flows. Okay, then we can see either the current is within the limits of this equipment capacity lah. Okay, that's is power flow. Then why the power flow is important? This is for planning for expansion of the power system network, to open new factories, new industries center or and so on lah. Okay, for planning. And then for operations, we want to know what is the current values, voltage values, and so on. Then for scheduling and exchange of power between utilities. Let's say we have this one, let's say Malaysia, we have Thailand. So Malaysia and Thailand is connected through the DC transmission line. Okay, so Malaysia usually sell power to the Thailand utilities at night, and then during the day Malaysia will buy power from the Thailand utilities, okay, through the DC transmission line. Okay. So to know how much power needed by Malaysia, there we have to run the power flow based on the specific load size. Okay, that's why we have to study the power flow. We have to know how much power is needed by Malaysia during the day and how much power is needed by the Thailand utilities during the nights. Okay, something like that. Okay. So usually power flow is required by many other analysis such as fault analysis. That's why I said before we run the analysis, we have to run the power flow. Usually to make sure that our model in any software is right. We want to check our design is correct or not. We have to run the power flow before we do other analysis such as fault analysis, transient stability analysis, contingency analysis, and so on. Okay, these faults to calculate fault current, transient to see, let's say this is transmission line, we have the circuit breaker. Okay, this circuit breaker. So when this fault occurs to this transmission line, this circuit breaker will open. Okay, when the circuit breaker is open, we want to see the voltage waveform of this network. Let's say something like this. This switching situations, we have to monitor to see either after the fault clear, let's say something like this, fault current is quite high. After the fault clear, what happened to the voltage? Let's say this current, we have voltage waveform. What happened to the current and voltage waveform during the transient time? Maybe within this microsecond, what happened to the voltage spark? Either it's so high, we have to eliminate the spark, although or eliminate the current sparking. Okay, that's why we have to study the transient. This is study within a second or milliseconds. Transient stability study. We look at the waveform of the current and voltage. Okay. Contingency study also the same. So let's say this transmission lines is disconnected. What happened to the other transmission line? Other transmission line can cover or can supply power to the other network or not. Okay, let's say we have system like this. Okay, this one. Okay, usually we have this motor. Let's say this transmission line is disconnected. This disconnected. So how power is being transferred to this bus bar? Okay, power can come from this line, and then at the same time, power can come from this bus bar. Okay, if this line is connected, what happened to the current flow from this line? This current flow is still within limits or not? If not within limit, we have to isolate these loads. Okay, we have to disconnect this line also. That's why we have to study the contingencies. If this line is open, which line should we open consequently lah after the disconnected of the line lah. Okay. Usually to make sure that that system is stable. Okay, because last time in Malaysia we have the major blackout. Okay, major blackout occurs I think around 1980 something. I didn't remember. What happened is, let's say we have some generator. We have many generators actually. We have many generators supplying the loads. This is the grid system, Malaysia grid system. Supplying the grid system like this. We have many generators. Some generators have problem. So this generator is disconnected. If one generator is disconnected, okay, this few generators can still supply to the grid. Okay, can back up the grid. What happens if many generators start to disconnected? Let's say this generator is disconnected due to the problem, and then this generator is supplying using its maximum capacity, and then this become very hot. This one also break down and disconnected from the network. We have few generators disconnected because of the faults occur on the transmission line. Let's say this fault occurs, all power supplied through the fault is this fault is not clear. This generator will become overload. Maybe one generator is broken. It's still okay. Other generator can support. What happens if there are many generators disconnected consecutively lah? Let's say after this generator disconnected, and so on. As long as this fault cannot be clear by the transmission line, by this circuit breaker, this generator is overload. When this generator overload, it will cause all the other generator also overload lah. And then because of that, all generator is disconnected from the network and cause the major blackouts in Malaysia last time. Okay. That's a contingency study. We have to make sure that when fault occurs, this circuit breaker must isolate the faults. If this circuit breaker cannot isolate the faults, other circuit breaker, backup circuit breaker must isolate the faults. Okay. If this cannot, other circuit breaker must isolate the faults. Okay. That's why we have to do the contingency studies. Okay. So how to develop bus admittance matrix? Okay.